Audio works, I can start.
Yeah, ready.
I'll give it another minute. All right, it is my honor to introduce Dr. Shanpeng Li. When I last met him, he was still Mr. Shanpeng Li, so he recently graduated from UCLA in 2023 in the Division of Biostatistics. Currently, he is a staff scientist at the City of Hope in the Department of Computational and Quantitative Medicine. I've known Shanpeng for quite some time now. We both have the same PhD advisor back at UCLA. During his time there, he did a lot of research in survival analysis, particularly with what he's talking about today in joint modeling. And he was also sort of part of the base unit or the biostat unit in the cancer center, providing statistical support to clinicians through that center. And so today he'll be talking about, I think, part of the work he did for his dissertation, right? On novel approaches to joint modeling of longitudinal and time-to-event data with applications to dynamic prediction of health outcomes using massive EHR data. So with that, I'll leave it to you.
Yeah, thank you, Eric, for the nice introduction. And today, I'm very glad to be here, give a talk, and share my research ideas with all of you. And yeah, so this is my PhD dissertation, and but even after I graduate, I still continue to like further extend this topic to be able to handle different kinds of EHR data. So yeah. Okay, so now let's start with the introduction of this topic. So there's many papers talking about the correlation between the longitudinal and the time event data, and they are first of all, they're very strongly correlated, and then we cannot just ignore the association between these two outcomes because we found that like some very important biomarkers that could be a strong predictor to the health outcome. For example, in the diabetes study, we are able to observe the longitudinally measured systolic blood pressure, and we found that this biomarker is a pretty strong predictive of the time to CVD outcomes such as stroke and any other disease. There's many papers talk about that, and then in the past, clinicians just use the separate analysis or two-stage modeling to just simply incorporate the blood pressure into a longitudinal covariate in the survival modeling. And then later on, many researchers find that these traditional methods will bring into bias issue and the invalid inference because of these two major issues I listed here. So the first one is a missing not at random mechanism in the longitudinal data due to a terminal event. So in summary, it means that, like, for example, if you observe a death of the person and then because the person already died in a clinical study, you won't be able to collect his biomarker measure after the event time. And other examples could be like if the person like drop out of the study, and then also you find it impossible to collect their biomarkers. But in fact, this kind of missingness mechanism is not ignorable. If we just want to use a linear mixed model to explain the biomarker, this modeling usually requires a missing at random mechanism. So in this case, we just apply this traditional method into the data set like this scenario that won't give you the reasonable estimates. Okay, so this is from the longitudinal standpoint. From the survival standpoint, okay, if we use the longitudinal covariates of blood pressure into the, let's say, for example, you use a Cox model to try to account for the effects of the blood pressure into the with a health outcome. We require this model to observe the covariates to be continuously. Okay, so that means that at each uncensored event time, we need to gain the biomarker value from the patients. Unfortunately, that's not the case in the clinical study because the patients only come to the visit on their own time schedule. So like each patient they come to visit to have a blood pressure collected in their own interest, right? So maybe for example, like the patient one, they came to the hospital on Monday and Wednesday, but you won't be able to observe their measures on Tuesday and Thursday, right? But if we use this traditional model, we may also require them to have the measure on Tuesday. Okay, so these missing data can also cause issue in the survival modeling. So that's why these two major issue will have the consequence. That's pretty bad. So in the past decades, researchers bring up the concept of joint modeling by jointly model the association between these two outcomes to first mitigate the estimation bias and correct the statistical inference. Okay, and lastly, we can use the framework of joint modeling to perform a dynamic prediction of the future event probability based on the history of the trajectory of the longitudinal biomarkers. So compared to the traditional modeling, we incorporate all the available historical information of the longitudinal observations to help us strengthen the prediction accuracy of the time to event. So this is the basic idea of using a joint modeling nowadays. Okay, so we know that there's a tons of papers talking about this topic, but more importantly it's very important to have okay, so so where are we? So just now I talked about there's many research talking about this topic, but more importantly for the clinicians is to have a user-friendly software to run their models, right? So now I provide you some examples of the R packages to run all different kinds of joint models. So here I would like to split the available software into two big chunks. The first one is the parametric version, and the second one is a semi-parametric. So how do you differentiate these two? We just simply look at how the baseline hazard is specified in the modeling framework. If, for example, if the baseline hazard is totally unspecified, then we need to choose semi-parametric package to run the model. Okay, so for the parametric one, one of the most commonly used package in this area is a JM package because it has many different kinds of assumption of baseline hazard for you to choose to help you find out the more appropriate model you want to run this data. Okay, so JM is based on the frequentist framework, and instead, if you are like a Bayesian guy, of course you can choose a Bayesian version of the joint model. For example, you can choose JM base to fit a joint model in the presence of a single time to event. However, if you have multiple, a single time to event and a single longitudinal biomarker. However, if you have multiple biomarkers in your data set you are interested, okay, you can choose the JM base too. Okay, these two packages basically come from the same team. Okay, they just want to extend the framework into different scenarios. Okay, and then for the semi-parametric, we can choose joining R, JSM. All these packages are based on the non-parametric baseline hazard, but they probably have a different association structure in their model. And the last two I highlight in both phase is the one I developed based on my thesis. So if you are interested in the joint modeling, so you can feel free to try out these different packages. Okay. Okay, now let's dive into the introduction of the EHR data. So as you guys all know, there's a many massive biobank scale EHR data available for you to conduct health studies. For example, when I was back at UCLA, I used to work with the UK Biobank dataset to support my method. So the total sample size for the UK Biobank is like more than 480K. The other one I used to work with is a million veteran program. So this program basically monitor the health status of their diabetic status of the veterans. Okay, so our interest is to look into the diabetes complication once they diagnosed with diabetes. We want to find out which kind of biomarkers are potentially associated with this disease outcome. Okay, so with the utility of all these different EHR data, we are able to perform first, identify important risk factor, okay, from the parameter estimation point of view. And second, we are able to perform adverse event prediction by running the model, and then we have the predicted value of a given at a given future time point. What's the probability of developing that disease given the information you have here? And finally, we can use this predicted value to have personalized medicine development. So that would be a pretty good instruction for the clinicians to talk to their patient, to talk about how to prevent this disease, even though they have the disease, how they are able to fight against it. So in analyzing the large scale HR data, of course, sometimes we may have computational and statistical challenges. The first obvious issue is a large sample size. Okay, so many biobank data, they probably have a 100,000 or even million of patients. Okay, so if we just use a traditional joint model to run this data, sometimes you may not get the result in real time. Okay. So the second could be the heterogeneity of the measurement error of the longitudinal outcomes. Okay, so these two are the challenges, and today I just give you guys an idea of how to overcome this within this modeling framework. Okay. So as I just said, the current joint model development is lack of efficient implementation because of the large scale HR data. So because of the unaffordable computational costs. Okay, so in the first chapter of my thesis, we propose a method called customized linear scan algorithm under the semi-parametric joint modeling framework. Okay, our goal is to relax the computational burden from at least O(n) squared to linear order. Okay, so the rationale is the idea is quite simple. So the rationale is to require all the observation times, the survival time, to be sorted descendingly by taking the advantage that the risk set is decreasing over time for the right sensor data. Okay, so the purpose of doing the data sorting is to avoid the repetitive calculation of risk sets, especially if you want to get the updates of your baseline hazard and also the particularly the survival fixed effects. Okay, so you might encounter this kind of complex computation. Okay, so however, after applying the linear scan algorithm, we are able to speed up the estimation procedure by thousands fold if we have more than this amount of sample size. Okay, so the result of using this algorithm is to reduce the runtime from days to even minutes for the big data. Okay, so my package FastJM is using this approach to run the UHR data. Okay, so now let's dive into the modeling framework first. So from the longitudinal standpoint, so first let's look at the notations briefly. So we have subject I from 1 to n, and we have a different clinical visit J from 1 to ni. So each person may have a different visit schedule. So here we also have the possibly time varying covariates to explain the outcome. Okay. And we also have the fixed effects of these covariates. So this is typically a regular setup of a linear mixed effect model by introducing the random effect, the subject-specific random effects to explain the individual mean trajectory. Okay, so these are the common assumptions that has been made in the mixed effect model setup. Okay. Okay, now let's look at the survival part. Let's define TI and observe event time, and we also have DI from 1 to K, the indicator of failure type. So joint model can also account for the presence of competing risk. So if you have multiple event you're interested in, so the competing risk event is defined as whichever event occurs first, we observe first. So this is the setup. Okay, so for each failure type, we have the specific proportional hazard model. Okay, so for each failure type, we have the completely unspecified baseline hazard, and we also have the vector of survival time invariant covariates. Okay, and lastly, we have the latent association structure. So how do we interpret this guy? So this guy, MI transpose T, is the components coming from the longitudinal part. Okay, so besides this traditional setup, we introduce this guy to account for the relationship between the survival and the longitudinal outcome. Okay, so how do we specify the latent association structure? So here I give you some typical examples. Okay, so these are the commonly used parameterization. So first is a current value. Okay, current value means like we bring up the whole mean trajectory, okay, to correlate with the survival outcome. Or we can use the first derivative to correlate that. Or we can use the latent the current value of latent process. So basically we bring over the individual mean trajectory, okay, to correlate with the outcome. Or more simply, we can use a shared random effect setup. So basically we use the BI, the random effect from the longitudinal parts, to correlate with the survival outcome. So this is highlighted because this is the one I'm going to use in my thesis to show you how the joint model is able to handle the big data. Okay. So now let's talk about the likelihood of the joint model. So let's define psi as the full vector of all the parameters you are interested in. Okay. And we have of course, y and c are the both outcomes we're going to jointly model. So then we have the assumption that these two outcomes are independent, conditional on the autocovariates and the random effects. Based on this assumption, we are able to write the observed data likelihood. Okay, so the data likelihood can be simply written as the product of the data likelihood from the longitudinal, the likelihood from the survival, and the prior distribution of the random effect BI. Okay, so based on this assumption, it's very easy for us to write down that likelihood. However, maximizing this observed data likelihood is non-trivial because of the presence of the baseline hazard. Okay, so to overcome this issue, we develop a customized EM algorithm to derive the MLE. I think EM algorithm is very well known to solve the problem of missing data in your modeling. Okay, so in the E step, we're going to calculate the conditional expected value of the log likelihood, the complete data log likelihood, and then after we calculate that, we're able to do the M steps. So we update the parameter estimates in the EM iteration. Okay. Okay. So let's briefly talk about the E step. So the E step involves calculating the expected values of any functions of BI that appears in your likelihood. Okay, let's say any function HBI that is written as the integration of the HBI with respect to the posterior distribution of the random effect. Okay, so how do we calculate this guy? Well, now we have different tools for doing this job. So first we can do the Gauss-Hermit quadrature method. So Gauss-Hermit quadrature, we have two versions. So first is to use a standard version. Standard version is quite simple. It's quite straightforward. We can just use the prior distribution of BI to calculate the quadrature points. Okay, for you to build up the support to calculate the integral. Okay. Alternatively, this team developed a fast version doing the Gauss-Hermit quadrature by using the posterior distribution of random effects given the longitudinal to help you calculate the quadrature points. Okay, so using this trick, we are able to reduce the number of points. Why reducing the points is important? Because the computational burden of the step grows exponentially with respect to the number of points you choose for the integration. So now the thing is, if you use the less number of quadrature points to get the reasonable accuracy, that would be great for your analysis. So today we're going to use this procedure for the model. Okay. So talking about the M step, some of the parameters like beta from the longitudinal, sigma square, and the covariance matrix of random effects, and also the cause-specific baseline hazard, we are able to find the closed form solution. Okay, by simply picking the first derivative. Okay. However, other parameters, especially from the survival covariance fixed effects, okay, they do not have closed form solution. Okay. In this scenario, one thing we can try is to use a one-step Newton-Raphson algorithm. Okay, to keep it updated in each EM iteration. Okay. Okay, so just now is talking about the parameter estimates. So now let's talk about the standard error. Because the presence of the unspecified baseline hazard, it's very difficult for us to get the standard error by getting the second derivative of the complete data log likelihood. So instead, what we can do is to find the first derivative, okay, of the complete data log likelihood, and then use a profile likelihood, okay, to get the information matrix, facial information matrix first, and then we take an inverse to get the standard error at the end. Okay. So this is one method for getting the standard error. Okay, so now let's talk about the computational aspects within the EM algorithm. So just now I talked about the E-step. Okay, so this is the computational burden that appear in the E-step. So it would be great if we can lessen the number of points we need for the integration. Okay. In the other aspects, okay. So just now I mentioned that because of the non-parametric baseline hazard, we need to account for the repetitive computation of risk sets. We call it RT in the EM steps. So in the parameter estimate standpoint, the computational burden is ON squared. In the standard error, it even goes to ONQ. Okay. So this is obviously a computational bottleneck. If your sample size is larger than like 10,000, okay, it won't give you the estimate in the real time. Okay. Because of the presence of the risk sets. Okay. However, we can use the fact that the risk set is decreasing over time for the right sensor data. The risk set calculation is simply just a series of cumulative sums along with the uncensored event time. Here we call it, the greatest one is T1 and the smallest one is TD, let's say. So the solution to this computational bottleneck is just to develop a linear scan algorithm with the following mapping. Okay. However, we have a condition for the linear scan algorithm is that we make sure that the things inside the summation over the risk set must be time independent to get the algorithm work in the modern framework. Okay. Okay, let's give you an example showing you like how to apply this mapping. So given if any time t greater than t prime, the set at t prime consists of the observation from the RT and the set of the observation from this time interval. So here we can split this summation into two different summation over different time points. So here we can use this fact to apply the linear scan algorithm to further relax the computational burden over the risk sets at each uncensored event time, okay, to make the computation to be linear in total. In the standard error estimation point of view, we even have like a double summation over two different risk sets, okay. However, we can still use a similar idea to relax the computational burden of this guy into a linear order also, okay. But because of time, I'm not going to talk about the details of computation. I mean, if you have interest, just look at my paper. We have the detail to describe like how this algorithm works. Okay, so here, let's give you the simulation results applying this algorithm. So here in the panel A, we can see like three different methods. Okay, so the one highlight in red is a traditional method. Naive method. And the second method, which is highlighted in green, is to just use the pseudo-adaptive Gauss-Hermit quadrature, but not our proposed method to run the model. And the one in blue is a method that uses the pseudo-adaptive Gauss-Hermit quadrature plus the linear scan algorithm I developed here. So here you can easily find the time difference as the sample size goes large from 100 to 100,000. You can see that the full change of the time cost grows non-linearly. Okay, so here, especially for the panel C. So here we can find the computational gain from using the linear scan algorithm to handle the large size data. Okay. Okay.
Are you saying on the large scale?
Yeah.
So it is rising very fast.
Yeah, it's quite fast. So like, for example, if you look at the sample size of 100,000, the runtime is about like 1,000 seconds. Yeah. However, if you use a traditional method, that will cost you like 100 times more than the method I developed here. Yeah, and if you want to go further, like 1 million, the two traditional methods won't even work in a real time. So you probably need to wait like a couple months or even a year to get that, like in a worst case scenario. Okay.
Well, that's why they have parallel.
You mean these two?
Well, I don't know.
Okay.
Parallelize.
Oh yeah. Yeah, the method I propose here is linear over the sample size. Yeah. Okay, so yeah, so this plot talks about the comparison in the standard error estimate. Okay, so if we just naively implement the profile likelihood approach without any linearization, so in this scenario is the one is this curve, the blue curve. Okay, you can see that even if the sample size is not very large, it's just 10,000, the runtime for getting the standard error just costs you like around like 100,000 seconds. However, the method we propose here just costs you like no more than 10 seconds, I guess. Okay, under this sample size. Okay, if you want to go with a larger sample size than this, you won't even get the standard error in the real time. Okay, so yeah, so the right panel show you the full change of these two over these two methods. Okay, so we can see that the runtime of the naive method grows non-linearly. Okay. because the y-axis is the log scale. So, okay, so here is an application study. Okay, just now we talked about the data resources of UK Biobank. So luckily, I have a chance to touch this data. So this database has around 200. Yeah.
Good question. Sorry. So I think the linearization is amazing because it reduces the computation time substantially. In the small sample case, we're able to verify that your results are the same using both approaches. Like to estimate the standard error.
Yeah, it's
up to some epsilon.
Yeah.
Accuracy.
Right. Yeah, it's essentially the same. Like whether or not you apply this method. Yeah.
Okay.
Because we just modify the computation of the risk sets. Okay, so which one comes first, which one comes later, right? So, but in theory, it won't be any numerical difference, right? Yeah. Yeah. Okay. So here I would like to apply my model to a UK Biobank data. So in total we have around 200,000. So here I use a existing R package to have a comparison. So this is also a semi-parametric joint model. Okay. So here we have a different subsets. So the first example we use is to randomly select 5,000 subjects, and the second example is to select 20,000 subjects, and to compare the time cost between these two methods. So amazingly, we can see our package are able to handle the data, run the data in the linear order as the sample size goes large. However, this model is not able to get a result if you throw the whole data set into their model. So either like a memory issue or the machine issue. But yeah, but eventually, like only our package can run this type of data set with a large sample size. Okay. So just now I talked about the computational aspects. So now I would like to talk about another aspect. Okay. So what if our longitudinal outcome has a very high biomarker variability? So this is one thing we are interested in. So because previously most of the joint model focused on the individual mean trajectory of the longitudinal outcome. Okay. But very few study talking about the variability. So today I would like to talk about how this plays into role. Okay. Yeah. So there's many historical clinical trials especially about diabetes. They talk about the within subject visit-to-visit variation of the longitudinal biomarkers. For example, glucose variability and blood pressure variability that could be potentially predictive of the CVD outcomes. Okay, so here I would like to give you an example from the real data we analyzed before. So the left panel is the longitudinal profile of the systolic blood pressure with a very high within subject variability. You can see the curves is pretty much lie in the big range, like from 100 to 200. Okay, for these randomly selected participants. Okay. However, we also look at the ones with low within subject variability. We can see the range of their the variation of the SBP is around like 80 to 130. Okay. So this is the observation we got from the real data. And if we just keep saying that only the individual mean trajectory influence the survival outcome, this assumption may not be hold. Okay, in this real data. Okay. Okay, so in the past, people, of course, the many research explore the variability of the biomarker to this health outcome, but most of them are based on the two-stage modeling approach. Okay. However, there's some practical and theoretical drawbacks about this two-stage modeling. So two-stage modeling means like in the first stage, you use a mixed effect model to get the estimates. And then you use the results from the stage 1 analysis, like you get some individual covariate like random effect, this kind of thing, to be a survival covariate into the stage 2 analysis to get the result. Okay, so this two-stage modeling, of course, have some drawback. First, we need to have a sufficient number of repeat measures of a biomarker to enable us to get a reasonable estimate in the stage 2 analysis. Second, this modeling also requires the non-informative truncation of the longitudinal observation. Okay. However, just now I just mentioned to you at the beginning, because of the terminal event, this assumption is very easily violated. Third, the estimation bias from the stage 1 analysis cannot be accounted for in the stage 2 analysis. So that if we have if we observe the variance from the information in the stage 1 analysis and bring that over to the stage 2 analysis, so this modeling approach won't be able to account for the estimation variance from the stage 1. Okay, so fine. And the last point is, if we ignore the correlation between the random effects of the individual mean trajectory and the biomarker variability, that could also lead to the biased results. So the motivation behind all this issue is to have a joint model to not only account for the individual mean trajectory, but also the within subject variability. Okay, so now let's look at the model formulation again. Okay, so instead of assuming the homogeneous individual variance, so here we introduce an equation to model this guy instead. Okay, so here again we use a very similar equation as you can see in the mixed effect model setup to model the logarithm of the within subject variance over time. Okay, and then the epsilon I is the unit independent measurement error. Okay, that is the same across all subjects. And then we have because the omega I in this equation we specify as an individual random effect. So here we have like a joint random effect we call theta I to be a joint vector of the random effect from the mean trajectory and the one from the variability. Okay, and then we assume it to be normally distributed. Okay, so this is the new, the new thing in the mixed effect setup to account for the variability. Okay, and then in the survival setup, okay, we bring over the longitudinal information from both of these aspects to influence the survival outcome. Okay, for example, in the latent association structure, if we use a simple setup like a shared random effect approach, okay, so we can just incorporate this guy, the random effect of the variability, to have a we are going to estimate the effect of that with the survival. Okay, and then the assumption are basically is essentially the same as the chapter 1 I just talked about. Okay. And then the estimation procedure is essentially the same. You can continually use the EM algorithm and the profile likelihood approach for the standard error. Okay. Okay. So after we propose a new model, we're interested in seeing the prediction point of view. Okay. So now let's briefly go over the dynamic prediction in the joint modeling framework. Okay. So relying on our goal is to use all the historical information of the longitudinal observation to perform a dynamic prediction of the health outcome. That would be very helpful to make a better clinical decision. Okay. So the objective is for any new patient I star who has not experienced the events at time S. So S we call it as a landmark time. Okay. We are going to predict the probability of experiencing the clinical events before time U is a future time which is greater than S. Okay. We call it horizon time, based on the historical information yi star of S. Okay, so this is our notation. Okay, so for each failure type, we are able to calculate the the probability that the new subject's event time will happen before time u for a specific failure type. Okay, given that they're all alive at time s, and they all have all the available information before time s of the longitudinal. Okay, and then we integrate out the cumulative incidence function from s to u divided by the conditional survival function at time s, and then we integrate this guy with respect to the posterior distribution of random effects theta I given these information. Okay. Okay, so now let's look at the simulation to see how this new model, this new joint model compared to the classical ones. Okay, so here our goal is to simulate the data sets in the presence of heterogeneous within subject variability, and then we apply these two models and see how the performance look like. Okay, so this is the details of our simulation setup from the longitudinal, and this is for the survival. Okay. So model 1 is our proposed joint model by accounting for the individual within subject variability. Okay, and yeah. Oh, okay, sorry. Yeah, I just go faster. And the model 2 is a classical model by holding assumption of homogeneity of the variance. Okay. So this table show you the computational performance between these two models. As you can see in model 2, we are able to see the very obvious bias because of the presence of within subject variability. Okay, and this thing will cause the much lower convergence probability. Okay. Okay, so just now we talked about the estimation. Now we talk about the prediction point of view. So here we use the prediction accuracy metric is fourfold cross validation mean absolute prediction error between the predicted and the empirical cumulative incidence rates. Okay, so we use this metric to evaluate the prediction performance of the model. Okay, so I guess most of you should know about the cross validation. So basically, for each validation set, we are going to perform the prediction, and then within each. So here in the validation sets, we are going to split the subjects with different risk groups. Okay, so for example, the dark blue one is the patients with a very high risk based on the predicted value we calculate from the joint model, and then we use the predicted risk to compare with the empirical risk provided by the Kaplan-Meier estimates. Okay, and then within each risk groups, we are able to calculate the difference, the absolute difference, and then we integrate that over all the risk groups for a validation set, and we keep doing that the same manner over each box of validation. Okay, so this is the metric we propose to evaluate the performance. Okay, so in the simulation, we are able to see the decrease of the prediction error using the proposed model, the model 1. Okay, of both failure. Even though the failure 1, you might see just a little bit decrease, but in failure 2, you are able to see the larger decrease. Okay. Yeah, so because of time, just quickly go over the application data. So here we use a MESA data set. We're targeting the patients with the when they came to study, they all free of clinical CVD events, but eventually some of them would develop CVD events, or even some of them would die. Okay, in the study period. Okay, so here we apply these two different models. Okay, so here you can see the very important takeaway message is that when we account for the within subject variance, we are able to adjust for the effects of individual mean trajectory. That turns out to be non-significant. However, we are able to see the increase of the within subject variability over time. Okay, so this is one very important information, like compared to the classical joint model in the right panel. Okay. So this is from the estimation of the longitudinal. So here is the results of the survival submodel. So here we can see that, okay, so the hazard ratio of the within subject variability is pretty large. Okay, so how do we interpret this hazard ratio? So here I have a small note here. So it means that one standard deviation increase of the SPP variability will lead to around 100% more higher risk of both clinical events. So yeah, so this is how we interpret the hazard ratio. Okay. However, in the right panel here, you won't be able to get that information. Okay. So this is example of looking at different risk, two different groups based on their different within subject variability. We can easily see that when we plot the empirical CIF function, the one with the higher within subject variability will cause more probability to die in the study. Okay. And lastly, we use the prediction accuracy metric I just talked about applied to these two clinical events. We can see that, especially for the death, okay, using the model I proposed, we are able to see the higher the accuracy of the prediction. Okay. Okay. So here's the discussion. So today I use I talk about two perspectives in the joint modeling framework. So first, we need to have an efficient implementation of the joint modeling to be able to handle the massive data. And second, we should also model the biomarker variability to increase the prediction accuracy. Okay. So a list here is the future work I'm going to work on. So because of time, I will just stop here, and thank you all for listening.
You have time for some questions?
Yeah, very nice work. So the computational answer really impressive. You mentioned that your method is still semi-parametric, but I wasn't clear about how you dealt with the non-parametrically with the baseline hazards, because you showed a full likelihood. I didn't see any partial likelihood or anything like that, so I wasn't clear.
Oh, yeah. Sorry, because the derivation, the details is very lengthy, so that's why I didn't include in my slides. But basically, if you want to get a closed form solution of the baseline hazard, you need to use, for example, in the cost modeling strategy, you might need to use a Breslow estimator. So you can find out the very explicit analytical solution, and you can easily find that there exists a repetitive risk set calculation. Yeah, so that's the reason why the many semi-parametric joint model has a computational issue. Yeah.
I have two kind of questions. One based off the application, the other one is based off the method. So the method you're doing is this like linear scan, right? Linear risk set scan, which I think is ideal. It makes sense when you have non-tied survival data. But what happens when you have tied survival data, or the event times are tied? How does that affect the estimation? Because like for the Cox one, there's like three ways, right? There's like the Efron, Breslow, and exact method to handle ties. So how do you take into account ties in the computational approach for the linear risk set scanning?
Yeah, that's a very good question. So in the risk set calculation, we focus on the specific discrete supports that is based on all the unique distinct event time. So our risk set calculation is based on only these uncensored event time. Okay, even though some of the patients they have exactly the same event time, our risk set calculation is just based on this support only. Okay, so for this tie situation, I don't think the when we scan the algorithm will be a problem. We are still able to account for the tie situation.
the second question I have was based on the NACE study. So you had two outcomes, you had death and heart failure.
Yeah.
My assumption is that heart failure doesn't equate to death. People can have heart failure and then still live afterwards, right?
Yeah.
So in that case, death is more so death prior to heart failure, right? Not, because then, like in the pathway, you can have heart failure and then die.
Yeah.
Right, but then you don't view that part, you just view the first event.
Right.
Because the second one is a semi-competing risk.
Yeah.
So in this case, death is more so heart failure-free death. That's sort of, it's either heart failure or heart failure-free death.
Yeah,
Right?
it's a very good point. Yeah.
Got it.
Yeah.
So,
Yeah. Yeah, but I think, of course, some patients, after they experience a CVD event, it is also possible for them to experience that, just because of the higher risk compared to other people.
Yeah.
So I think a potential extension of the joint modeling is to also account for the semi-committing risk. That would be the special case of multi-state processes. Of course, there's a many literature talking about the multi-states. The simple case is semi-committing risk, but we can even like further generalize it. Okay, so this is another approach. But in my impression, all the existing literature just focus on the individual mean trajectory instead of the biomarker variability. I think this is another area you and me are able to like explore on that. Yeah, based on this. Yeah.
There's another dynamic prediction model, the two-stage model, where first stage has it being a longitudinal model. Does that require your data to also be matched to the same observations, or can you use the summary statistics from UK Biobank as the first stage model to create a prediction into some other sensor data, similar features, or does it have to require batch observations for both?
Can you clarify like the match observation?
Like the same observations that you follow longitudinally with match with their time to event.
Mm-hmm.
Can you use the longitudinal as like a summary statistic from another source of data, your time to event, or?
Yeah. I mean, like, yeah, this is typical the use of the two-stage modeling, right? Like first you use the longitudinal information to fit a mixed effect model, and then use a useful information from there, and then to be incorporated into the stage 2, the survival modeling, and then to get the effects of the longitudinal history to the survival outcome. Yeah, you can absolutely do that because this approach, of course, it is very fast compared to the joint model. Okay, and however, we encounter these practical drawback because the assumption is violated. In non-informative data truncation, this assumption is violated because of the terminal events. So eventually, you might be able to see some bias, especially when you have a large sample size. Yeah. So that is a potential issue of using the two-stage modeling, or the landmark modeling. So you just, yeah, of course, you can use a two-stage modeling to make prediction using the stage 2 model, right? Based on the recent observed longitudinal observation to be one covariate to account for the risk of the clinical events. Of course, you can do that, but I guess again, the bias issue cannot be mitigated. Yeah.
Okay. All right, we're right on time here, so let's thank the speaker and thank